Before I start this video today, I just wanted to give a huge thank you to all you guys who have been watching my videos so far. The reception has been incredible, and I really enjoy interacting with you guys in the YouTube comments and the Reddit forums. And do let me know if there's anything you're interested in or any topics you want me to cover, because I'm certainly interested. Please like, subscribe, and enjoy. So we've looked at basic pendulums before, but today I'm feeling a little crazy. Let's get it.
Solve that single pendulum, bruh. What did he do? I think I'll order me a double, but let's add something new. Josh the old arms, we gonna add on some strings. Newton himself wouldn't dare come up with such things. Make the mortal humans tremble, but I know of a guy. He goes by sympy, solve within the blink of an eye. Let's do While we be getting to work, we'll be saving some trees, cause we gonna do this using our PCs.
I know I promised I said there'd be no paper this video, but I do want to take a brief minute or so just to go over a few things to set up the problem. This is a picture of our pendulum. We're going to take this as the origin. Now obviously there's a few coordinates here. The coordinates of this bob we're going to call x1, y1, and this one we'll call x2, y2. So there's four free variables in this case, x1, y1, x2, y2. But it's obviously in some ways easier to express this problem in terms of other things. We can also express it in terms of the following two angles. Theta 1, which I'll call like this, and theta 2, which I'll call like this. And you think, well, what are the other two? Well, the other lengths are going to be the stretched lengths of the two springs, which I'm going to call R1 and R2. And using this, we have all the information we need to know about the relationship between these variables. I know, for example, that x1 is equal to, also there's the unstretched length of the pendulums, which I'm going to call L. So these are called L. Now I'm going to do a little trick here. Okay, and this is common in physics with these sorts of things. Instead of putting L, I'm going to put 1. Just the number 1, right? And you may think, well, why are you allowed to do that? Well, what I'm doing here is I'm saying that everything in my problem is measured in units of L. So L equals 1 is my dimension. It's like setting h bar equal to 1 or c equal to 1 in physics. It sets my dimensions so that R is measured in units of L. X and Y, they're dimensionless now. They're measured in units of L. G, the gravitational constant, is measured in L's per second square. So it's unitary, and I'm allowed to do this. I'm allowed to set one of my dimensions equal to 1 in the problem. So from this I get x1 equals 1 plus r1 cos theta 1. X2 is just x1, which is with that above, plus 1 plus r2 cos theta 2. And I get similar things for y1 equals minus 1 plus r1 sine theta 1. And y2 is equal to minus 1, I'll just call it y1 minus 1 plus r2 sine theta 2. So this is everything we need to know about our problem. Let's solve, shall we? So we have our packages today we're going to use. NumPy and sympy, of course. Sympy being the symbolic library we're going to use for our symbolic math. We're going to use SciPy to integrate the ODE so we can eventually plot the solution to the system. And then I have some matplotlib to make an animation. So like before in the previous video, using sympy, we first need to define our variables. And the four initial ones would be T for time, M for the mass of the two pendulums, G for gravity, and K for the spring constants. We're assuming that they have the same mass and the same spring constant. So to do that, I go T, M, G, K. I'm defining all four at once. Is equal to sympy.symbols. And I just go T, M, G, K. And I need to import the packages. And you'll see that if I print one of these, for example, M, I get M, and I can do things adding them together, and it'll store these in little formulas like that. So these are the basic variables. Now we need to define these 4 free variables, theta 1, r1, theta 2, r2. And these are functions of time, right? And we're going to compute them, and then we're going to also define their first and second derivatives, and this will come in later. So I'll do this for 1, and then I'll skip ahead for all, since we're doing the same thing for each of the 4 variables. So the first thing I'll do is I'll go theta 1, theta 2, r1, r2 is equal to sympy.symbols. And in LaTeX notation, I have theta underscore 1, theta underscore 2, r1, and r2. And these are going to be functions of time, so I have to be careful that I go CLS equals simp.function like this. So now they know that this will be a function of some other variable, right? And I can define them as functions of time, for example. So I'll just do one variable and then I'll skip ahead to the other. So I'll go theta 1 is equal to theta 1 of t. That makes it a function of time, as you can see here. And then I can define the first derivative, and I'm going to use underscore d for one derivative and dd for the second. Go simp.diff, this is the derivative method. And I just go theta 1 t, and I'll define the second derivative as well. Underscore 2d's, and this is just differentiating the first derivative with respect to time. So now I have theta 1d, and theta 1dd, the normal function, first and second derivative. And now I'm going to skip ahead and do them for all the others. Okay, so you see I've done the same thing for all 4 of the variables. I have theta 1, theta 2, r1, and r2. And I can find, for example, the first derivative of r1. Once I run this cell, I can find the second derivative of any of these. So they're all defined now. Most of this is just defining things. And so the next thing we're going to do is we have our r and theta coordinates, and now we're going to define our x and y variables. And x and y, of course, are functions of r and theta. So Bob 1 is located at x1, y1, Bob 2 at x2, y2, and x1, y1, x2, and y2 are all functions of theta 1, r1, theta 2, and r2. So defining these, we have x1, y1, x2, y2 is equal to simp.symbols, and then LaTeX x1, y1, x2, y2, and we're going to go to make sure that they're functions, right? And now we just make sure that they're all functions of the necessary things. So x1 is only a function of theta 1 and r1, and y1 is a function of theta 1 and r1, but x2 and y2 are, of course, also functions of theta 2 and r2, as you can see in the diagram that I have on the side. So here I can print, for example, x2, and you'll see that SymPy writes this really nicely. It's x2, and it's a function of theta 1, which itself is a function of time, r1 which is a function of time, theta 2 function of time, and r2 which is a function of time. So we know this, and we actually can define these since we have formulas for this. So x1, of course, is equal to 1 plus r1 times simp.cos theta 1. And you can see that the general structure is pretty similar for all 4 of these. y1 is just a sign here. And I'm going to write minus sign based on how this is described. And x2 and y2 are defined similar. Here I have a 1 plus r2 cos theta 2. And then this gets repeated for y2. I'm just putting in the formula you see on the side. And here we are. We've defined x1, y1, x2, y2. So for example, I can print y2, and it has exactly what you would expect for this formula here. So we're good. So now we can define the Lagrangian, which is really easy. And T and V are just given like this. So we have the potential energy, the kinetic energy of the both systems. This is the Bob 1 and Bob 2. And we also have the gravitational potential and then the potential stored in the strings. So this is really easy to define. I can just say T is equal to 1/2 times M times, and it's just simp.diff x1 T, square this, same thing with, so we have x1, y1, and then of course x2 and y2 as well. I'm just gonna make sure that this is on all nicely on one line. So x1, y1, x2, and y2. So that's our t. And now, of course, we'll define v as well. So v is equal to m times g times y1 plus m times g times y2. It's k times r1, 1/2 k r1 squared plus 1/2 times k times r2 squared. And then L is equal to t minus v, the Lagrangian. So I can print L, for example, and it's a long one. It's not an easy function, and it's expanding everything in terms of theta 1, r1, theta 2. So it's a pretty big beast. You can see now why this would be pretty difficult to solve on paper. But as you'll see in the future, I'm basically going to show you that this is impossible to do on paper unless you have a million years, which we don't. So here's our Lagrangian. Now we're going to compute Lagrange's equations. So there's going to be 4. Remember, there's a Lagrange equation for r1, for theta 1, for r2, and for theta 2. So let's do that. So I'm going to call this LE1. This is the first Lagrange equation, and it's simp.diff, and we're differentiating L with respect to theta 1 minus derivative of L, well, it's simp.diff L theta 1 d, and then remember that this is the dl d theta 1 dot, and then we're differentiating this with respect to time. So it's a derivative of a derivative. That's what's going on here. And then we're going to simplify this. And you'll see how long this is. It's a beast, I'm telling you. Now if we print this, this is our first. Remember, there's 4 of these. Here's our Lagrange equation. Yeah, pretty big. Not something you want to be doing on paper, writing out this every time. Okay, so we've done it for 1. I'm just going to skip ahead to when we have all 4 complete. All right, so we now have all 4 of our Lagrange's equations, and of course I can print LE3, for example. And something to note that's going to be really important for us is, although this is really complicated, the second derivatives only show up as linear factors ever. So if you have a second derivative of theta 2, it's only like a constant. It's not squared or anything. Same thing with r1 and r2 and theta 1. The second derivative is only ever linear. And that's nice for us for this particular system. It means that we can do the following. So remember, if we have a second order differential equation, right, we can turn it into 2 first order equations. And the example I have is here. I would take a look at this example. You have dy squared dt squared plus 2 dy dt plus y plus 3 equals 0. That's a second order ODE. But if I define a new variable, v equals dy dt, then we get 2 first order differential equations. And that's dy dt is v, and dv dt is minus 3 minus y minus 2v. Go through that and you'll see. So it requires defining a new variable as the first derivative, and they're coupled. The 2 differential equations are related, and this is how we solve them in Python. So in this, you'll note in all 4 of these Lagrange's equations, we have second order derivatives of theta 1, r1, theta 2, and r2. And we have first derivatives of those 4 variables as well. So for each one of those, I'm going to let z be an arbitrary one of those 4, so z can take on any of these values. We get 2 equations per free variable, because remember, we have second order differential equations. So vz is dz dt. Remember, z can be any one of these. So defining this, we get the following equations. We get dz dt is vz, that's our first equation, it comes free. And dvz dt, which of course is the second derivative of any one of these, is what we're going to solve for. And you think, well, what are we solving for? Well, remember, if I print this, right, the second order derivatives only ever come as a linear factor. So we can solve, so if these 4 Lagrange equations, it's essentially a system of 4 linear equations for these second derivatives. So we can solve for each of those 4 second derivatives. It's a system of linear equations. Yeah, this looks nonlinear and everything else, but in the second derivatives, it's linear, and that's a huge advantage. And we have 4 of them, and then they're linearly independent, and we can solve for the second derivatives. And we get a second derivative for each. Remember that dvz dt is the second derivative of z. So we'll solve for each of these in our 4 equations, and then we'll have 8 equations that we're going to have to put into our ODE solver. If you're confused about this, pause the video and really replay it a few times and think about what's going on here, and consider this example. So rather than Vz as dz dt for all of them, I'm going to define omega 1 as d theta 1 dt. Omega 1 is analogous to Vz in this case, and same with omega 2, V1, and V2. So we have 8 variables now. We have theta 1, theta 2, R1, R2, and omega 1, omega 2, V1, and V2. So we're going to have 8 systems of equations, and we're going to plug them into an ODE solver eventually. So this is the most complicated part of the video. So let's actually find our second derivatives, because remember, to set up these ODEs, we need these dvz dt, or in other words, d omega 1 dt, d omega 2 dt, which are the second derivatives of the regular ones. So for this, I can use sympy.solve. And we have 4 equations here. We have our 4 Lagrange equations. And what are we solving for? We're solving for theta 1 double dot. Remember, second derivative of theta is d omega 1 dt. That's going to be one of our equations. We're also solving for theta 2 dd, r1 dd, and r2 dd. To make this go faster, I'm going to choose simplify equals false and rational equals false. Otherwise, this takes a little bit long to solve, and it turns out it doesn't matter in what we're going to be doing later. And I have a dot here. And I need to make sure I have theta 1 dd. So here's the solutions. Solves pretty quick. Now, this is really where you see this is impossible to do on paper. Watch this. I take my first solution. And I have to index, by the way, with the variables. So I say, I want the solution for theta 1 double dot. Watch this. Look at this. And let it load. Do you think that you're going to deal with this? Look at this. Do you want to be doing that on paper? I don't think so. I don't think so. Look at this. It's making my computer lag. Disgusting. Sympy. Huge expression. But we can do this. We can solve this. We can turn this into a numpy function. And we can actually solve for this. We can make this into a function. Right, remember, this is one of our ODEs. It says that the second derivative of theta 1 with respect to time, or in other words, d omega 1 dt, which is one of our derivatives, is equal to this. So we're going to use this as our function. So this is why this is a no paper question. You can't do it on paper. If you can, send me a message. Show me how you did it. But I don't think so. I don't think this is possible. So we have our solutions in sympy. Now we're going to turn them into numpy functions, so we can do this numerically. We've done it symbolically so far. Now we're going to do it numerically. So again, I'm going to do it for one, and then I'll skip ahead to when I solve them for all. So d omega 1 dt is a function. We're going to use this lambda phi. So this takes a symbolic expression and turns it into a numerical expression. We're going to use this lambda phi. And what does it take in? What does that big equation I showed you take in? Well, it certainly needs m, k, and g. It needs theta 1, theta 2. It needs r1 and r2. It needs theta 1 dot, theta 2 dot, r1 dot, and r2 dot. These are all the things that big expression takes in. And the function, of course, we haven't specified the function yet. This is for, so I'm going to say, function is solutions, theta 1 double dot. So what does this mean? This here, I'm indexing this array. I'm saying this is the function, and these are the variables that are passed into the function, and it turns it into a numpy expression. So now we have a numpy function. And d theta 1 dt, this is easy because I've defined a variable. By the way, underscore f for function. That's why I'm doing this for numpy. This is also simp.lambda phi. Plug in theta 1 dot. And it returns, the function is theta 1 dot. So this is the input argument, and it returns itself, basically. That's the same as like dy dt equals v. It's taking in something, and it's just spitting out what I put into it. Okay, so I'm going to do this for all 4 variables now. Okay, so I've made it for all 4 variables now. We have d omega 1 dt, d theta 1 dt, d omega 2 dt, d theta 2 dt. So we have all these 4 differential equations, and then of course the simple ones, the dy dt equals v, or in other words, the dz dt is vz, right? So that's just saying, for example, d theta 1 dt is equal to omega 1, right? These are these equations here. Very complicated, so there's 8 of them, and 4 of them are really those big ODEs that we can't solve by hand. Now watch how fast this can be solved in NumPy, for example. Okay, so now we need to define our system of ODEs. We have 8 variables here, and we have 8 coupled differential equations. And we'll define this as our vector s. And remember, to solve this in Python, we have to take in a function. We have to write a function that takes in s and returns ds dt. So I'm going to define ds dt, and it's going to take in s and time. So it takes in our vector s, and it needs to return stuff. So firstly, theta. I'm going to define this here. Theta 1, omega 1, theta 2, omega 2, r1, v1, r2, v2. This is just equal to s, so I don't have to index every time. And it's going to return. First thing it's going to return is d theta 1 dt, this function. And it takes in omega 1, right? Of course, and it returns that. So d theta 1 dt is omega 1. That's simple. And the second one is d omega 1 dt f. And it takes in m, k, and g. Remember, this function takes in a lot of things. It takes in theta 1, theta 2, r1, r2, v, and remember that these derivatives here are just omega 1, omega 2, and v1 and v2. So omega 1, omega 2, v1 and v2. And so that's like that. And now I'm going to do it for all 4 of the variables. Okay, so now I have our system of ODEs for all 8 of them, so I can run this cell. And we're going to define our constants and times, and we're going to solve our ODE. So t, we're going to solve for 1,000 times between 0 and 20 seconds. I'm going to set g is equal to 9.81. I'll say m equals 1 kilogram, k is 10 newtons per meter, and our answer is ODE int. We pass into s dt. Our initial condition, which I'm going to say is, we'll say the first is np.pi over 2, no angular momentum. Remember, this is theta 1, omega 1, 3, so I'll go 3 halves times np, 3 halves. This is theta 2, omega 2. R1, I'm going to put as 0, but there's going to be initial velocity, so v1, it's initially being pulled apart, 5, and same with the other one, r2 and v2. And I'll put in my times, and we let it solve, and we should get an answer. Takes a little bit to run, but of course the system is pretty complicated, and we're done. So plot theta 1 as a function of time. Well, remember, our answer looks like this. If we want to get each of the 8 variables, we index them like this, so we have to transpose it, and 0 gives us theta 1, 1 gives us omega 1, theta 2, omega 2, etc. And I can plot theta 1, for example. And you see a pretty complicated looking motion, right? It's not, certainly not straightforward, right? Somewhat complicated. So now we can get the locations of x1 and y1 and x2 and y2. For that, we need to take these expressions for x and y and turn them into NumPy functions. So I'll just write a function like this. So I'm going to call it define get x1, y1, x2, y2, and it'll take in theta 1, theta 2, r1 and r2, and it's going to return them in this order that I've defined them here. So it will return 4 things. The first one will be, so I'm going to paste this here. And we just need to basically turn these into NumPy functions. So rather than the sympy stuff, we just turn it into NumPy. So instead of simp, we have NP, 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 NumPy like that, and they're all defined the same like this. So now we can get our x's and y's. So x1, y1, x2, y2 equals get x1, y1, x2, y2. Remember that this is theta 1. This is theta 2. Remember, it skips over because we have omega 1 and stuff. This is R1, and this is R2. And I need an underscore here. And I need and of course I need to add commas here because this is a tuple, a simple mistake here. And now I have my arrays of x's and y's. So I can plot everything, of course. For example, I could plot y1 as a function of time. And you can see it does somewhat of a bizarre behavior. So now let's make an animation. I have animation code. Again, I don't want to go through it too much, but I will briefly talk about what it does. So we set up a plot figure. We make an ax. We have a line that's initially set to nothing. We set our limits. And what happens is at each frame, we're going to set the value. So we have 0, x1, x2. So it makes a line connecting 0, x1, x2 and 0, y1, y2. So it's connecting those points using x1 and y2. And it's going to connect it at that particular frame. And so note what's going on here. We have 1,000 frames. We're saving at 50 frames per second, right? We also have 1,000 times between 0 and 20 seconds. That means we have 50 frames per second, right? 1,000 between 0 and 20, that gives 50 of those frames per second. So if we plot it at 50 frames per second, we're plotting it in real time. So I can run this. Okay, and after about 30 seconds of running, we get a GIF, and we can play it. And sure enough, we get something that looks like a double pendulum with 2 springs. A very complicated system to solve. Totally undoable on paper. But we did it in sympy, we used no paper, and we saved probably about 1,000 trees based on how long that equation was. Anyways, thank you for watching. I encourage you to play with this code. I'll put it up in the GitHub as always. Try maybe, making the masses different, for example. That's a good challenge. Or making the lengths different, the spring constants different, and see what happens. Play around with it, do whatever. I've sort of done the very basics with this system, but there's a lot else that could be done. Anyways, as always, if you like this video, please like and subscribe. Thank you.